Okay, so I'm going to talk a bit about model parameters. So when you create your model in Virtual Pulse, it'll kick out an OpenStudio model, which will have a lot of default assumptions in your model parameters. Some of these you're going to want to keep. Some of them you're probably going to want to get better information on. So before I do that, I'll talk a bit about how Energy Plus does some of the calculations. So look a bit under the hood of Energy Plus, and that will help us determine what parameters we're going to want to look at. So as I had mentioned in the prior lecture, that Energy Plus is a simultaneous integrated solver. So we have information, our weather information, information about the windows and the walls and surface heat balances, and we can combine that with information about our HVAC equipment and how that's distributed in the building. And the heart of that is the air heat balance manager. So we have our zones, which need a certain load, and the balance of that is what Energy Plus does, and which will give us our temperature that we have in our zones and the cooling and heating supply that our HVAC equipment is providing and its energy use. So the zone balance, you again have probably seen this before if you've done a heat transfer class. So we have our air in our zone, and again this is the energy stored in the zone air. We have the sum of all our convective internal loads. We have the convection at all of the surfaces in the zone, and we have a term for the infiltration. This is between zones, and this is from the outside. And then lastly, we have the input from our HVAC systems. So we'll talk about terms in sort of each of these parameters, and together they will sort of build up into this zone thermal balance. So the first one is the outdoor information. So to get that information into Energy Plus, it accesses a file which is called the TMY file. TMY stands for Typical Meteorological Year. There are other files that you could use. You can use an AMY, which is an Annual Meteorological Year, and that's the actual data for a given year. The TMY file is taken at a specific site, and they take the average month over a 30-year span, and they take those average months and combine them together to form an average year, and that constitutes the typical meteorological year. And so that is what we use when we are doing our energy simulations, especially projecting forward, because we don't have future weather data. The other piece of information that we need to include in our model here is the geometry. This will give us the number of zones, the building shape, and the orientation. So this is something that you will have set with the Virtual Pulse interface, so you don't need to change this in the actual energy model, and you've already done it with Virtual Pulse. I would recommend, though, if you want to recreate your model, to stick with the window-to-wall ratio of 0.15 to 0.25 for now, unless you know your building is very far away from that. You may have also assumed a construction when you were building your Virtual Pulse model. These are things that you can and maybe do want to change in the OpenStudio model and using a different template. The way that Energy Plus handles it is that there are two types of surfaces. It has exterior surfaces, which have heat transfer across them to the outside, and it uses specific algorithms for that. It also has interior surfaces, which it uses for thermal storage. So some of the energy use, or some of the energy that's coming in from, say, solar gain, is convected directly off the wall, and some is actually stored in the wall and convected off at a later time. The constructions are composed of layers of materials, and I'll show a bit about that on the next slide. And one thing to keep in mind, in the energy simulation, all of the surfaces with the same orientation and properties are lumped together in the calculation. So the way that this mostly comes to bear is if you have a lot of windows and they're all facing a certain direction, Energy Plus is actually going to combine them together and really not keep them separate unless you're using Radiance or some specific daylighting software. So it's okay to make the assumption that your total window area on a specific wall for a specific zone, as long as the areas match, that's okay. You don't need to have each individual window. So as I had mentioned, that constructions are composed of layers of materials. So in this case, each of these materials is a layer. In this case, this is an acoustic ceiling tile that we have here. We have some airspace, and then we have some concrete. So this might be a floor construction for a wall. I'm sorry, it's vertical. It should be horizontal. But this is in the reference if you're interested in seeing how Energy Plus actually handles that. But you'll need to put in all this information, or you don't need to put in all this information about conductivity, density, specific heat, etc. You can change those values if you want, but that's sort of unnecessary. If you were modeling, say, a specific material or some sort of phase change material that you wanted to include, maybe you would adjust these parameters, but you don't need to do that for your models. Those are referenced in the material properties in the ASHRAE Handbook of Fundamentals if you are interested in getting specific values for those. Okay, so we talked a bit about construction, and part of what goes along with that is the infiltration. At each exterior surface, you're going to want to specify a certain infiltration value. And what that is, if you're not familiar with infiltration, is that there are lots of different holes and cracks in a wall, and as you have wind coming by, some air from the outside is going to come into the building and some is going to leave. And also in the winter, if you have a lot of warm air in your building and it's very cold outside, there will be a buoyancy effect, which will cause air in your building at the top. There will be a pressure differential there where it will want to escape, and cold air will want to come in at the bottom. The last thing you'll have is induced fan pressure from your HVAC system, and that will tend to pressurize the building relative to the outside. So you have these sort of three main different sources of pressure in your building, and if you combine them together, that will give you the pressure field across a certain exterior surface. And if you know information about the characteristic of the holes there, then you can get the amount of flow that is going across the surface. So Energy Plus handles this in sort of three different ways, and you can pick which one you want to use. For this class, I don't have a strong preference for which one you use. The first is just a design flow rate, so you'll have some sort of schedule for the infiltration and some known value. And there are just some parameters here. These are pre-programmed default sort of parameter values, A, B, C, D, and that's correlated to the temperature difference and the wind speed. Another one that you can use is effective leakage area, which is saying that for a certain amount of wall area, there is this amount of holes. And you can use, again, your temperature differential and your wind speed with sort of known coefficients with some schedule, and that will give you your infiltration. The last one is really specific. If you know for like a specific hole or a specific wall assembly your flow coefficients, then you can calculate that using information about your wind speed and your temperature difference. So typical values for infiltration. Infiltration is sort of notoriously difficult to measure in buildings, but people have done it, and I would recommend using these databases. This is not something you'll be able to measure in your building itself, but these are typical values here. These are amount of air per unit time across a certain surface area. And you'll see for buildings on the UMD campus will have a lot of masonry buildings, and they are offices or school buildings, so they are generally going to be within this range of, say, between 20 and 40 meters cubed per hour per meter squared. So there's some current research that's going on now to try to take all of the flow information that you have for each zone and have the infiltrations be specific to each zone rather than just sort of assuming a default. And it's really great if you can use this. Their sort of integration is just coming out with Energy Plus, so I'm not expecting you to use it for this class. But one thing I will mention of those is they still sort of use default assumptions for leakiness. So it might be a bit more accurate in terms of which facades have sort of which infiltration sources, like when wind is changing, for example, or temperatures are going to vary by zones in the building. It might be a bit more accurate about getting your infiltration values there. But it's still sort of assuming a default assumption for the leakiness. So what I recommend you use in your models is, again, in that range of 25 meters cubed per hour per meter squared. And that's referenced to 75 pascals. If you want to get that value for a different reference pressure, then you can just use this equation. And this is also described in the Handbook of Fundamentals if you want more information on that. So the last thing that you'll have in your OpenStudio model are these sort of templates for different space types. So you might have conference rooms in an office building and an open office and bathrooms. And for each of those different space types, you can specify your plug load densities, your occupancy densities, domestic water use, schedules for all of those things, your lighting levels, your temperature set points and your controls and your ventilation parameters, etc. So what I'd recommend doing is in your OpenStudio model, sort of create your own template, which you're going to call, say we're in Martin Hall and it's Martin Hall classrooms, and that's going to assume assumptions for all of these parameters for classrooms in Martin Hall. And I'll go through each of these sort of what are typical values which you can use for those estimates for different space types. So plug load, this is it's going to be a key parameter in your model. It's about a quarter to a third of the energy use in newer buildings. So as you can imagine, a sort of small difference in that is going to create a rather large difference in your total energy use. So be careful with these assumptions and be careful with these schedule assumptions. How Energy Plus does it, it's very simple. It's a watt per square foot value that you'll have for a specific zone, and it will have a schedule associated with that. And so you can choose what that schedule is, and you can change that value, but that's sort of the amount of control you have over the plug loads. Yeah, we can determine this from interval data, and you'll be getting that later on when you're ready to approach calibration, and you can come back and edit your plug load assumptions. For now, I would use a default assumption, which you can pull off this graph if you're interested. This is for an office building in Philadelphia, or you can use some other assumption from the reference buildings that DOE has put together, or from ASHRAE or something like that. This is specific to computers, so for those who have computer labs in your building, this will give you, again, a picture of what is a typical plug load profile that you can expect. And again, it'll be different on weekdays and weekends, so make sure you have different, that your templates and your schedules account for that. The other thing about plug loads is that just like a radiator, when you're standing next to a radiator, you feel some heat coming off. Some of that's going to be radiant, and some of it, if you're above the radiator, is going to be convective. So the radiant portion that's put off by, say, a radiator or, say, your computer, some of that's going to be absorbed by building surfaces and furniture in the room, etc. and some of that's directly going to go to the air, which is then seen as a load for the HVAC system. So we can calculate what the HVAC system sees in present time by taking 1 minus all of the fractions, like latent or the radiant or fraction that is just generally lost, to get what our HVAC system is seeing in that moment. The rest is going to be stored and it's going to be re-emitted in, say, 15 minutes from now or an hour from now. And it will, the HVAC system is smart enough, or the Energy Plus is smart enough to know when to release it, or when to release that energy back into the zone, or convect it back into the zone. And this is sort of an example of that with a thermal camera. You can see this is in the long wave spectrum. And so you can see this is the radiant energy that's coming off of, again, these computer monitors and these laptops. So that's being absorbed by surfaces and will be re-emitted in, say, 15 minutes from now. And there's sort of a default value for what that radiation is. Energy Plus assumes 0.2, and I suggest you keep this at that value. If you want to try to change that, if you think that your loads are very different from convecting a lot of heat and they're much more radiating a lot of heat, then maybe you can consider changing that, but I don't recommend that. So the other major energy user in buildings, especially office buildings and educational buildings, is the lighting use. So there are set values for that, which you can find in ASHRAE standards. This is to code, and your building might be better than code, or it might not. It's, again, something that you might want to check. And this is just sort of a watts per square foot. And again, there'll be a schedule for that, so similar to plug loads. So you have a watt per square foot value for your zone and schedule, and that will determine the amount of lighting energy use that's occurring at the zone at that particular time. UMD's policy has a specific light intensity policy that it follows for offices, classrooms, labs, hallways, stairwells, and restrooms. So you can do some calculations to figure out what this means for your building. I would be careful of assuming this as a default because this, first off, this policy was relatively recent, and second, there can be like lots of variations just even in a given classroom depending on when the building was built. So you could start with this as a default, but then try to make sure that you check out your building to see if this actually is a good assumption. Now, similar to plug loads, there's a certain amount of lighting, the energy use in lighting is then goes into the zone air. Some of that is convected and some of that is radiant. And that is going to depend on the type of lighting it is. So if lighting is recessed into the ceiling versus if it's suspended from the ceiling, those are going to give different amounts. And there's just a table in the input-output reference that you can check, which I've copied here. So you can look at your building and see what sort of lighting system predominates. I think recessed lighting is probably the most common on campus. So you can use those fractions for recessed lighting. The temperature set points, another major parameter that you're going to want to look at in your simulation. So UMD has a policy to keep it between 68 and 78 degrees Fahrenheit. This is just a policy for what the temperature set point should be. Again, this is not what actually your building may have the temperatures set to. And there might be a lot of stratification with air, and which will cause the controllers to run a bit differently. They think it might be a lot hotter than it actually is in the building because the thing that's measuring that is on an upper floor where all of the hot air is going. So just keep that in mind. If you can find out a good assumption for what the actual controller is measuring for your temperature, so maybe you can try to figure out where that is. If it's just in the return air, then that should be pretty simple. You figure out where your most of the largest return air vents are, and see if you can get a measure of the temperature at that point, and that should give you a rough idea of what the temperature at that point is. If you want, you can try to capture that over time and maybe get a better assumption there. And we have some tools in our lab to do that, just some quick data loggers, which I assume you're welcome to use. So stop by and we can give you one of those and you can check it for your building. Another one you want to look at is the design ventilation. So for each building, there's a certain amount of fresh air it has to provide per each document. And this can, there's a bunch of ways you can sort of do this. One is to assume a certain value per person or per floor area or per zone, or a total amount of air change per hour. I think that the best way to do this is probably per floor area. That's the way I think a lot of actual mechanical designers do that, is they just assume a set value per floor area because you don't necessarily know your occupancy. So you can assume sort of a 0.1 to 0.2 CFM per square foot, or 20% of the total design flow rate, one or the other. And this is specified in ASHRAE 62.1 if you would like to look at that. So the HVAC systems. Your building is probably not going to have a typical HVAC system since it's on campus. I think a lot of these buildings have heat exchangers with a steam system, and then that hot water goes to some heating coils in your air supply. So double check your HVAC loop to make sure that it makes sense. You may be able to use one of the default systems and then just do calculations on the back end to figure out what the total steam load should be or the total chilled water load should be. And there's good tutorials online for how to do those changes in OpenStudio. But generally the way that it works is you have sort of a series of nodes and you're connecting them together with different pieces, and you're going to have some sort of central HVAC systems that are feeding into those loops, as they are called, which then feed your zone. So you can make different assumptions about the piping in here. I think most of this is going to be adiabatic. You can put in pumps, you can put in different fans and return air fans, and OpenStudio is pretty good about the interface for that. So play around with that and come up with a sort of a good approximate model for the HVAC system in your building. There are mechanical drawings available. If you want, some of those are on the modeling resources. They're also available in the facilities management archives if you would like to access those for your building. Most of the buildings at UMD, again, are going to have that steam to hot water heat exchanger. I think most are continuous air volume, although some of the newer buildings have variable air volume supply air fans. I think there's a lot of DX cooling and there's a lot of chilled water as well. And that's going to be specific to your building, and it may have both. So choose carefully. I would suggest using the default efficiencies and the load curves that are provided in the software for specific equipment types. You can change those later on if you want and if the calibration calls for it. I'd also suggest auto-sizing the equipment for now, rather than trying to figure out what the capacity is. That may matter for your simulation, but I would suggest you keep the auto-size first and then do a few iterations of your sensitivity analysis and your calibration before coming back to that if it is actually important. So that's all I have on the model parameters, and I wish you luck in figuring out what those are for your building.